is someone were to give you a function like this. Right there. And they would ask you, if you were to draw that, would it have any punctures or holes in it? Is it continuous? And you would say, well, it's continuous everywhere except where? Where what's what? Everywhere except where x squared equals y squared. That's where you would have a problem, right? But these numbers are not in the domain, right? And that's what this is saying. All rational functions are continuous on their implied domains. The implied domain of this is everything except the numbers that satisfy this. What does that look like geometrically? X squared equals y squared. X equals y would not be allowed to be in our picture, and x equals negative y would not be allowed in our picture. So our domain would actually be everything in here, everything in here, everything in here, everything in here. That's what it would look like. I wonder what that would look like if you graphed it. Be kind of interesting. You would have a bunch of dipping down and going up. Should we see it? I just kind of made that one up. Plot 3D. What was it? X squared plus y squared over x squared minus y squared. I'll go negative 4. There you go. Oh, there it is. Okay, so look, the computer is having some issues. It's having some issues, right? So I'm going to do a couple of things to make this look a little bit nicer. First, I'm going to take the mesh out. I don't like the meshing. And then what I'm going to do is I'm going to force it to plot more points. And let's try 25 first to see. That got a little bit nicer. Let me try 40. It's pretty easy to bring the computer to its knees here if you go too far with this. There we go. That's a lot better. Do y'all see that? Huh? Can you all see that? It's a little better? It's a lot better. Thank you. How about we do this? Range. Range. Let's go range 20. Oh, plot range. Oops. That didn't help. Well, you get the idea, don't you? You got the idea. If you look at it from the side like this, looks a lot like a rational function from Cal 1, right? I mean, sorry, from college algebra. Rational, but it's a big surface of them. So this is just, these like vertical pieces are like where the computer's like, I don't know what to do, so it draws a vertical sheet. You can't do that. How many of you remember graphing on your graphing calculator? A rational function will do something like this, and then it'll draw a straight line down, and then it'll draw the other side like that. That's exactly what's happening here with the computer. The computer is having a problem with that. So I'm going off, I'm sorry. I'm just trying to get you all interested in this program. Exclusions, and then I got to remember the syntax for this. Exclusions, x squared equals y squared. I think I may have messed this up, but I'm going to try. Okay, there we go. That worked. So what I did is I told the computer that if you ever try and plug in x squared equals y squared, to not do that, to take those out. I hate this stupid box they put around it too. What? There's a lot that goes into making it look pretty. Axis origin, 0, 0, 0. There we go. Okay, that's about as good as it's going to get. You'll see it now? See, I helped the computer not freak out anymore. That's what that surface looks like. So it's continuous on its implied domain. So as long as you're on the sheet itself, you're not going to have any weird punctures in it. It does become asymptotic, right? But it's not going to be like all of a sudden you're moving along and all of a sudden it just vanishes. It's going to be some sort of continuous sheet. Are we at the end of the notes? We are. And we have just, there's the homework, page 32. That's not a very big assignment there. Page 632, 5 through 13 odd. All right. We have, what, about 10 minutes, 12 minutes? I think that's just enough time for us to get introduced to the next topic. All right? I know, come on. It's Monday, right? Partial derivatives. Okay, so we've taken care of limits. We've taken care of continuity. The next thing that comes is derivatives. How many of you have heard of partial derivatives before? You've taken partial derivatives where? Where have you seen that? Physics? You're taking partial derivatives? Some in differential equations? Yeah, absolutely. So what the heck is a partial derivative? Well, we're going to try and get a visual of it to start here with functions of 2 variables, although the idea extends to functions of 3 variables and 4 variables. But it's really easy to see with functions of 2 variables. So we're going to begin by just reminding ourselves of what it was like in Cal 1. Right? This is a function of a single variable, f of x, y equals f of x. If we said, what's the derivative, what you'd do is you'd move to some point, you'd go up on the graph, right? And you'd calculate the slope of that tangent line, and the slope of that tangent line was the derivative, right? As I moved around, as I change the x value, the derivative's value changes. Right? Good? Nothing new there, right? The problem we encounter with functions of several variables is that we actually have 2 variables to start with. This makes determining a single tangent line difficult. So imagine, just for the sake of simplicity, that we're looking at that one problem that was the top of the ball, right? Just a dome. If I pick some point on this dome and I ask you, what's the slope of the tangent line? Why is that going to be sort of a confusing question? Tangent, I mean, just touches the ball at one point. Which direction, right? Like, what do you mean? Like, okay, so you got this dome, right? Here's the dome. And let's say my knuckle right there is a point. I put this line on it. I can draw a point that goes just through that point, right? I draw a line that goes just through that point, and I can talk about its slope. But then, you know, I could also have come up with the line that goes this way through that point, right? And so it depends on what direction you're in, doesn't it? Yeah? So that's what makes it a little more complicated. Look, when we're back on a sheet of paper, and I say, all right, go to this curve and pick some point and give me the slope of the tangent line, there's no other dimension where that line right there can pop off the page and start spinning around like this, see? Right? So this was okay because we were fixed, we were stuck. But in 3D, that thing can spin around. So because of that, we have to pay attention to the direction we're pointing. And what would be one particular direction that might be pretty natural for us to think? So, perpendicular how? I'm going to try and do a demo without hurting myself. So the x-axis is going out that wall over there, right? The y-axis is coming out over here. Yes? Z is up. There's a surface right here. I'm going to go climb up on the surface. I better bring this with me. Okay, so I'm going to go climb up on the surface onto a point. Okay, I know this might get dangerous. Hold on. Okay, so I'm up here on the surface, right? And there's some curvature to it, so I'm kind of keeping myself balanced on it. And I'm going to try and put this on that point that's on the surface. Which way should I point? Should I point over there? Should I point over here? Which way should I point? What seems natural to you?
Follow one of the axes.
Over what?
Follow one of the axes.
Okay, so follow one of the axes. So that x-axis went out that way, right? So why don't I rotate this? And so I'm going through that point, but I'm running parallel to the x-axis, right? Another way I could point, got physics going on up here, okay? So I could point parallel to the y-axis, couldn't I? Of course, I could do anything else too, but naturally it seems like down the same directions as the axes would be our first place to start. And that's where we do start. Does that make sense? Now later on, we realize that, it doesn't matter which direction you point. We have something called the directional derivative, which you can change that direction to whatever you want it to be. But for now, it's going to be parallel to the axes. So here it comes. Here's me standing on that surface. Do you see me right there? See me at that point? Yeah? Now, I've got my x-axis coming out this way towards you, which was like the room over there. And then over here, yes? And so first thing I'm going to do is I'm going to point down parallel to the x-axis, which should be like this. Why did that get smaller? So it's like I was standing up on there, right? And I came through and I cut through the whole surface with a plane, didn't I? When I cut through the surface with a plane, that means the y-coordinate on any of those points, right, is fixed. Remember, y is the distance from here over. I'm fixing that. So do you all see that? That's y equals a constant. Right? Your y-axis is along this back wall. I'm fixing that y to be constant. Do you all see it that way? If I fix y to be constant, then this plane actually cuts through my surface, and where it cuts through the surface, it creates a curve, doesn't it? Yes? So what I'm going to do now is so remember, y right now is fixed constant, right? Y is fixed to be constant. What I'm going to do now is I'm going to pull the actual surface out of here because it's just going to get in our way. And then I'm going to walk way down the y-axis, way down there, and turn around and take a look at it. And when I do that, that's what I see. Right? And this is a Cal 1 problem now. You have a curve, right? And we could very easily find the slope of that line, which would be there. And if I want to, remember y is fixed, right? Y is fixed. If I change my x value, I will move along this curve, won't I? Now I'm going to bring the picture back in because I think it's important for you to see where I just came from. There it is. I'm going to bring the surface back into this. Here it comes. Okay? So all I had done, I started the problem like this. I cut it through with the plane, right? Y is a constant. Took the surface out, came from way on this side, and looked at it. Why did I come on this side? Well, because that means these x values are positive to my right, and my z values are positive this way. If I were to have come in from the other side, then it would have been x negative values. So that's why I chose to look at it from here. Did y'all see it? Surface gone. There it is. Now, that was with me standing up on the chair, deciding to point in the direction that was parallel to the x-axis. But we also said, let's do the y-axis. So let's take a look at how that changes the problem. So I'm going to take that out of here, bring the surface back in, bring my point back to some reasonable position. There we go. And then take that out of there. Actually, I think I'll leave it there for a second so you can see when I fix an x value, the plane I'm cutting through with is running this way now, right? Perpendicular to the other one. So I'll take the other one out. I'll pull the surface out. And then I'll just kind of turn it and look at it this way. This curve lives more in like the YZ plane, doesn't it? YZ. I'm going to go walk way out to infinity and take a look backwards. Pull that surface completely out. And now I've got this. And that should have a tangent line. I don't know why I'm having trouble with that. Whoa. Oh, I'm pressing the wrong thing. Oops. X infinity. There we go. So now, if I change my y value, because x is fixed, right? Then I get this. So here's what it comes down to. When you have a function of two variables, to talk about slopes of tangent lines, you have to fix one variable to be constant. Right? Fix one. If you fix one, then we just get a curve back in, like we were in Cal 1. We fix x to be constant, something happens, and we fix y, we get something else. So I'm going to go last one back to the original picture. I'm going to bring this in. I'm going to show you both of them at the same time. But I think what I'll do is I'll take the planes out of there. And so we have, I don't know, did the planes help? Two different tangent lines, don't we? Two different tangent lines. So what we have here is, am I over on time? Okay, all right. I hear everyone packing up. I'm just making sure like class didn't end at 2:30. If I fix my y value, if I hold my y value constant, we call that the partial derivative with respect to x, meaning that x is the variable, y is the constant. If you hold the x variable constant, it's called the partial derivative with respect to y, and you get a different answer. Sometimes, not all the time. So that's where we will pick up next time. We will talk about this definition, and then we'll go through and we'll actually do some partial derivatives. Yes?
The tangent lines we defined, were they perpendicular to one another?
They were perpendicular to one another, yes. Uh-huh. Hey, and you tell me, if you actually have two lines, right? Those two lines should define a plane, shouldn't they? And so we actually don't have really a concept of a tangent line here. It's a tangent plane. It's a tangent plane. So imagine a basketball and you have a sheet on top of it. You move that around. That's what we have instead of a tangent line on a surface. Tangent plane moving around the whole thing. You only need one what? Partial? No, to define a plane, because one partial derivative would just give you a single